All right, so 18.9 and 18.10 for the report only. And then what did you get here? Tell me your rankings that you got. What's the strongest? Oh, no, oxidizer on the left. Copper, too, so far? Anybody get silver yet? Silver is the strongest?
Yeah, I got silver.
Silver. So silver, and then copper, and then hydrogen. H plus, that's correct. And then lead 2, and then zinc 2. And so this would be the table so far. And then we could get the conjugate reducers. Silver would be the worst reducer. And then we need 2 H's, H pluses to form hydrogen. So hydrogen as a reducer falls between copper and lead. And zinc metal here is the not the weakest, actually the strongest reducer so far. And then we could just keep going and add more items to the list as we take more observations. So this completes the first part of the table. We'll just continue from there. All right, that's all I want to say about experiment 18. Let's go on to, what are we doing there?
The system.
Chapter 7, sorry. I just need to check one thing here. So far I told you about the first law. What's the first law of thermodynamics? Yeah, that's one way of thinking about the first law, but that's not complete, actually. So far, up to now, well, up to now, energy is conserved, right? Energy is neither created nor destroyed. Up to now, we have not had to worry about work. The reason we have not had to worry about work is because I made sure we didn't have to worry about work, right? I just made sure we didn't get too complicated, so I picked the problems that didn't have any work involved. But from now, we want to be able to do, either problems that have work involved, or be able to distinguish if we have to worry about work or not worry about work. And so let's talk about work for a moment. What types of work are there? When we think about work, we think force times distance, pushing something.
Yep.
Sometimes pushing things or lifting things would be called mechanical work, Like, for example, if I had a movable lid on my system, to pull the lid up, does that require work?
Yes.
Yeah, either to pull the lid up or to push the lid up is going to require work. And so mechanical work is one. What else? What else is electrical work? It's not objects, so we are pushing an object, electrons. We push electrons through a circuit, or pull electrons through a circuit. Does that require work? To pull electrons through an electronic circuit? Yes. That's going to require work. That's electrical work. What else? Chemical work? We'll talk more about it. Chemical work,
Reaction.
like doing a reaction. Usually when we do that, that would be called electrical work, like pushing the electrons to get something to react, something to consume those electrons, or pulling the electrons from something gets that thing to react or lose electrons. And so that's in this category of electrochemistry, I think, maybe. So there, we'll just say etc. So those are common things. And so let me give you an example of doing work. Inflating a balloon. If we blow up a balloon, that's going to require work. Right? How much work is required? And so let's talk about that. The amount of work required is equal to, not force times distance. It's going to be how big of a balloon do you want to blow up? The bigger the balloon, the more work. And so it's going to depend on how big you blow up the balloon, delta V. And one more thing. Not the molar mass, the gas. When you're blowing it up, it's going to depend on the pressure, the external pressure. That is, if you blew up a balloon in a vacuum, it's very easy. Just the balloon's going to expand. But if you blow up a balloon at the bottom of a swimming pool, it's going to be more difficult because you have to blow against increased pressure. You know, the deeper you go, the harder it is to blow. So in other words, the higher the external pressure, the more work you're going to have to expend in doing that work. Now, we have a sign convention for work. The sign convention for work is exactly the same as the sign convention for heat. That is, P external is always positive, right? And if we blow up a balloon, delta V would be positive also. And so if these two terms are positive, then we're going to get a certain amount of energy that we have to use to blow up that balloon. And so in other words, if we look at the system, and the system's blowing up the balloon, we're going to call this negative because the system has to lose the energy to blow up the balloon. And delta V here will be the change in the volume of the system. And so whenever we're doing these kind of thermo calculations, we got to worry about the system and the surroundings. And so, well, if the work of the system is, let's say, negative, then that means the work of the surroundings must be positive. Because if the system's volume expands, the surroundings volume must decrease to compensate. And so we're always thinking about that, and so we always have to have some frame of reference for this. But let's take a look at the units for this. The units of pressure are in atmospheres. The units of volume are typically in liters for gas, right? And so that's an atmospheres times liter. Is atmospheres times liter energy? And the answer is yes. Atmospheres times liter is energy. Well, then how much energy does it take to blow a 1 liter balloon against 1 atmosphere external pressure? Well, it takes 1 liter of atmosphere worth of energy. Well, does that unit make much sense? No, so we should relate it to units that we know. And so how can we relate this to joules? How can we relate this atmosphere times liters to joules? We need some kind of conversion factor, right? We can find the conversion factor in your book. It's in the back of your book. But you don't have to look it up because you already know it. You know? You already know it just like you already know the conversion factor from AMU to grams. And you already have it memorized, right? You already have it memorized because you know R. R allows us to figure it out because 0.08206 liters atmosphere per mole Kelvin. You know this R, right? Do you know another R? You probably should have this memorized. 8.3145 joules per mole Kelvin. Do you know these two R values? If you know these two R values, then you know the conversion factor. You can calculate it very easily. What is the conversion factor? Well, did you know these two R's are equal? Right? They're equal. They just have different units. And so what we do is we just take 8.3145 joules per mole Kelvin and divide it by 0.08206 liters atmosphere per mole Kelvin. And so the mole Kelvins cancel, and that gives me joules per liter atmosphere. And so what does it come out to? .32. 101.32 joules per liter atmosphere. And so in order to blow a 1 liter balloon against an external pressure of 1 atmosphere is going to cost you 101 joules of energy to blow that balloon. And so we can calculate the work that's required of this. Did we have to worry about work before? No, we didn't have to worry about work because the system volume never changed. So for example, our system was cold water, 50 milliliters of cold water, right? So if we have 50 milliliters of cold water, we pour it into the hot water and coffee cup calorimeter. Did that cold water volume change? No, it's still there. That 50 milliliters of cold water warmed up. But some people might say it did change because didn't we go from 50 milliliters of water to 100 milliliters of water? Didn't we? Yeah. No, we didn't, because the way we think about it is the system's still there. The system's an object. So the cold water warmed up, that was 50 milliliters. The hot water is part of the surroundings. That hot water cooled down. So half of it warmed up, the other half cooled down. And so we treat them separately. That 100 milliliters is actually 50 milliliters of system and 50 milliliters of surroundings. And so did the volume of the system change? No. Then we go on to the solid sodium hydroxide. When we added the solid sodium hydroxide, did the sodium ions grow bigger or shrink in size when we added it to the water? What do you think? Did the sodium ions grow bigger or shrink down? Did the hydroxide ions grow bigger or smaller by dissolving them in water? What do you think? Or do they stay the same size? What makes the most sense? Same size? Yeah, if you have a sodium ion here and you put it in water, do you think it's going to act like a sponge and absorb water molecules into the sodium atom and grow bigger? Does that make sense at all? No. And so, no, it should stay the same, right? And so did the volume change there? No. Really. If you look at it, yeah, the sodiums are now surrounded in a different environment. Rather than being in a crystalline lattice, they're dissolved in water. So in some respects, maybe the volume did change a little bit, but not significantly so. When you took 50 milliliters of HCl and poured that into 50 milliliters of sodium hydroxide, your system had 50 milliliters of HCl, 50 milliliters of sodium hydroxide, going to 100 milliliters of product. Did the volume change? No, it's 50 plus 50 is 100, and we end up with 100. So do you see that all the problems up to now, there was no change in volume, therefore we did not have to worry about any delta V of the system. If we have a delta V of the system, if the volume of the system changes, that is, if the volume of the system grows bigger, that's like blowing up a balloon. The system has to blow up a balloon, and it's going to require work. You know, if the system's volume shrinks down, then, you know, that's going to require work by the surroundings, because the surroundings now have to blow up the balloon to expand into that void. Does that make sense? Not at all? Okay, we're going to look at a specific example of that last part. But this is it. Well, let me do something there. If I take methane and 2 oxygens, so I'm going to just combust them. What are my products? My products are going to be CO2, gas, and water, H2O liquids. When I combust this is an exothermic reaction. Energy is released, right? And everybody can see that if I combust the methane here, somebody connected it to the vacuum. So here, energy is being released. Do you feel the energy? Maybe not, but I feel it. Heat, right? Definitely some heat is involved in this combustion of methane. But is there any work? Do we have to worry about work? I see plenty of heat. Well, I feel plenty of heat, right? But, well, up to now we didn't have to worry about work, but you know what? I'm sorry?
Because you mentioned before that work could be electrons being
Pushed through a circuit.
So could it be work in that sense that we're combusting something?
Well, there are electrons there, but they aren't being pushed through a circuit here. You could combust it to make the electrons go through a circuit, but we'll talk about that in just a minute. But do you know that there's work involved here? And how do you know that there's work involved? Well, what we have to do is we have to look at the volume. When I start this combustion, the methane and the oxygen, are they at, actually, what is the temperature of this? The temperature of that flame is like 900 degrees C. And so did the methane and oxygen start out at 900 degrees C? No, what did the methane and oxygen start at? The room temperature. Well, surely the CO2 and water that we just generated must be at 900 degrees C, right? But wait a minute, is it still at 900 degrees C? No. It's cooled down back to room temperature. And so where should we say? Should we say that the CO2 and water generated is at 900, or should we say it's at, we should say it's at room temperature. The reason we say it's at room temperature is because if we stopped at 900, like here, at 900, there's still more energy to be released to the surroundings. We got to be patient and wait until all the energy has been released to the surroundings, and we're back down to room temperature. So we were talking about this yesterday, remember? About that. Okay. All right, now, is that all heat? that's coming, this is an energy change. Is that all heat? Or is there some work involved? Now, how do I know? It might be all heat, but how can I tell for sure? Well, I look at my system and see, is there a delta V of the system? And so we have 1 mole of methane, 2 moles of oxygen. Do you know the molar volume of a gas at RT? What is it? What's the molar volume of a gas?
22.4 liters.
22.4 liters is not at RT, it's at STP. 22.4 liters would be at 0 degrees C. Are we going to burn our methane at 0 degrees C in an ice chest? Or maybe I could bring an ice chest in here, try to cool the air down. But no, that would be ridiculous, right? Or maybe plumb in a gas line into a freezer. That would be equally as ridiculous, right? We aren't going to burn it at 0 degrees C. Therefore, the molar volume of the gas at STP is worthless. You know how many times I've used the molar volume of a gas at STP? Maybe once, twice. What's much more useful? The molar volume of the gas at room temperature in 1 atmosphere. What is it? You have it memorized?
24.48.
Yeah. In other words, about 24 and a half. We're going to round it to 25. So it's about 25 liters of gas. So we have 25 liters of methane, and how many liters of oxygen? We have 25 liters of methane, and how many liters of oxygen? 50 liters of oxygen, which gives us a total volume of 75 liters. What did I just do there? Did I do a Dalton's law, or did I do an Avogadro's law? Did I do a Dalton's law or Avogadro's law? What did I just do? An Avogadro's law is valid under what conditions? Under constant pressure. Are we burning the methane at constant pressure, or are we burning it in a bomb? That is, constant volume. This is constant pressure. This is open to the air. Pressure is going to be atmospheric pressure. We don't even have to equalize anything. Right? It's not in the sealed container. If I burned it inside a bomb, then it would be a Dalton's law type scenario in which I shouldn't be adding volumes. I should be adding pressures, right? And so anyway, this is 75 liters, right? And we deal. You know why gas mixtures are so important? What is this? This is a gas mixture. If you don't understand gas mixtures, how can you do any chemical reactions? You can't. This is a mixture of 2 gases, right? How are you going to handle that? How do you mix them? And so anyway, okay, so we got 75 liters of gas here. And then we're going to, how many liters of CO2? 25 liters of CO2. And how many liters of water? 50 liters? No. Not 25. Not 50. Somebody tell me the right answer. Not 0. What? Yeah, we don't care about the water vapor. This is not water vapor. This is liquid water. This is why it's not 50 liters. This is not a gas.
Isn't that water vapor?
No, it's not water vapor. It was water vapor at 900 degrees C. At 900 degrees C, this was CO2 plus 2 H2O gas. And so at 900 degrees C, all that liquid water should be vaporized into the gaseous state, and then we'd say we went from 75 liters to 75 liters. But we can't stop at 900, right? What's going to happen? It's going to cool back down to room temperature. And what's going to happen to the gaseous water? Is water a gas at room temperature? No, water is a liquid at room temperature. And so tell me the volume of liquid water. We have 25 liters. So we got 75 liters as our initial volume going to 25 liters of CO2 and 2 moles of water. Which is 36 milliliters. Good. It's 36 milliliters. How did you figure that out?
Because 2 more water, the density of water is 1 gram per milliliter, so
Yeah, okay, 2 moles of water weighs how much?
36 grams
36 grams. 36 grams of water is,
divided by 1.
yeah, 36 milliliters. So that's it. And so, do you see that? We went from 75 liters to about 25 liters. 25.03, 25.04 liters. Right? Which means that delta V of the system changed. If delta V of the system changed, then is there work involved? Yes. Now, how do we deal with work? You know, it was hard enough just dealing with heat. And so how are we going to incorporate work into our calculations? Well, let's go ahead and deal with that. To deal with the work, we have to look at the first law of thermodynamics in yet another form. This is also the first law of thermodynamics. The first law says that, you know, any kind of energy change, so delta E of the system is equal to Q of the system. Q of the system is going to have a sign convention. Like, for example, if heat is lost by the system, you know, heat loss, we know that Q of the system must be greater than 0 or less than 0. It must be less than 0. It must be negative, right? And if heat is gained by the system, then we know Q of the system must be greater than 0. So any change in energy of the system is equal to the heat lost or gained by the system, plus, well, if the system has to blow up a balloon, then there's work involved, right? And so it's going to be the work of the system. The work of the system is the same sign convention. Work done by the system is negative. But we don't have to have work done by the system. Work can be done on the system by the surroundings. So work done on system by surroundings then the work of the system should be greater than 0. It should be a positive number. And so this is another statement of the first law of thermodynamics. Any kind of energy change of the system is going to be manifested in heat and in work. Okay. So far we've only looked at the heat part because we didn't have to worry about work, but now we have to worry about work. So the first law earlier holds, you know, Q of the system is equal to minus Q of the surroundings, because if heat's lost by the system, where did that heat go? Into the surroundings. So if heat was lost, then the surroundings must have gained. Or if the system gained heat, then the surroundings must have lost. Okay? Well, it turns out the work is the same way. Work of the system is equal to minus work of the surroundings, because if work is done by the system loses energy in doing that work, but the surroundings will actually gain energy. And if the surroundings does the work, then the system actually gains energy. If the surroundings loses energy doing work, the system gains that energy. All right, now we have to understand the energy in more detail. What do I mean by delta E? You know, this symbol we don't usually use, the energy, you know. In fact, we have something called the total energy of this. And that's what we're going to look at. U. Use the symbol for the total energy. Use the symbol for total energy, which is called the internal energy. And sometimes people think of the internal energy as equaling E. Depends on what book you use. Some books use E for the total energy. Some books use U for the total energy. Well, we're going to use U for the total energy. So here we have U initial. Here we have U final. Here we're going to have delta U. Delta U is equal to U final minus U initial. So if we think about the total energy, U, what is the total energy of a methane-oxygen mixture sitting at room temperature? Would you feel comfortable if I filled this whole room up with methane?
No.
You'd feel very uncomfortable because it's a high-energy mixture, right? And so the total energy of the mixture of methane and oxygen is high compared to CO2 and water. CO2 and water, are you going to get any explosions from that? No. So the total energy is lower. And so this is higher, this is lower. In physics, we know that the total energy is equal to what we call the potential energy plus the kinetic energy. This is the total energy of this. And so I have methane and two O2s. We look at the potential energy and the kinetic energy of that. So this would be initial potential energy, initial kinetic energy. And then the final energy here is going to be the potential energy final plus the kinetic energy final. Right? All right, so now what do we do? What we do next is this. The kinetic energy is related to what? Temperature. And so when we look at this, the delta U is equal to the change in potential energy plus the change in kinetic energy. And so the kinetic energy is temperature, and did the temperature change? No. The temperature stays the same. Therefore, delta EK is 0. And so this change in energy is entirely due to the potential energy. This is a high energy mixture. We call this the chemical potential energy. Methane and oxygen as a mixture has high chemical potential energy compared to CO2 and water. This would have lower chemical potential energy. And so for sure there was a change in potential energy. In physics, the analogy here is gravitational potential energy. This would be like methane and oxygen up here at high gravitational potential energy, and then down here at lower gravitational potential energy would be CO2 and water. So we see that here. All right, now the first law of thermodynamics says any energy exchanged with the surroundings will be in the form of heat and work. Was any work done here? Yes. How do I know that work is a factor here? the volume changed. And so there's definitely some work involved here. There are many ways that we can burn methane. Did you know that? Like we could burn it here in the lab. But we can also burn it in a CNG car. Have you seen those CNG, compressed natural gas cars? And so rather than using gasoline, they use methane and they put it into an engine. And when you put it into an engine, is it mostly heat, or do you want mostly work from burning it?
Work.
You want mostly work, and so you want to minimize the amount of heat that's generated. There's yet another type of vehicle on the road. The other type of vehicle is what they call a methane fuel cell car. Have you ever seen those? Methane fuel cell cars, they don't have an engine. What they have is a fuel cell. In the fuel cell, they convert the combustion of methane, you don't get any flames, they convert that into electricity. And so a methane fuel cell car converts this combustion into electrical work rather than pushing a piston up and down in a...
Is that more efficient? Is that more efficient? Is the methane fuel cell?
Yeah, much more efficient, actually.
Why don't we... That's awesome.
It's awesome, but the problem is the fuel density. If you fill your tank up with methane, you get 2,200 psi worth of methane in your tank, which means you have a range of like, they say the range is like 60 miles before you need another fill up. And so I was kind of interested in this, so I was looking. And so a whole bunch of people who have these compressed natural gas cars want to have a spare cylinder of methane in their trunk in case they run out of methane. It's illegal, but they're trying to jerry-rig some containers so that, because the filling stations aren't so nearby. And so one of the AQMD guys got on there and said, oh, you guys, this is all illegal. Don't do this stuff on the board, you know. And anyway, well, that's for compressed natural gas. That's for burning it in an engine. But for fuel cells, it's the same thing. You know, how much fuel can you carry? Liquids are much more dense. You don't have a bunch of empty space.
Wait, hold up. So methane is also known as natural gas?
Yes.
It's crazy. They made a supercar. It's rated at 1,500 horsepower. Its rate is absolutely terrible, but it's very powerful.
Yeah. So natural gas is not pure methane. You know, if you want methane, I was looking for just a cylinder of natural gas because natural gas is like 95% methane, right? But the only cylinder that I could find was research grade, 99.99% methane, and it was very expensive, so I didn't want to get it. But they used to have methane. A lot of people want on their boat. They want a natural gas stove rather than a propane stove. And so they used to have methane cylinders, but I guess that.
What's the byproduct of burning? Is methane burn?
Methane, does it burn? Boy, did you grow up in an electric household or what?
Why is it better to have methane than propane on the boat?
No, people just like the way it burns better. It's more like home versus propane. Propane, it just has a different flame characteristics. A propane stove versus a methane stove. It's just the way the flame burns. And if you look at that, for propane, the advantage of propane is you could store it as a liquid. Liquid. It's not too hard to liquefy propane. And so therefore, when you fill up a tank of propane, you got a lot of liquid propane in there, and it's heavy. Whereas methane is very hard to liquefy. I told you about, didn't I tell you about the that Southern California gas student at UCLA? Did I tell you that SoCal Gas wants to change from compressed natural gas to liquefied natural gas? No? All right. The gas company was over because I had a gas leak, and so the technician came over, and I started talking to the technician, and it turns out the technician is a chemical engineering student at UCLA, and he's working full-time, so it's unusual. Full-time employee for SoCal Gas being a UCLA grad student in engineering is very unusual. And then he told me SoCal Gas is paying for his education. So he got a job at SoCal Gas, and they liked him, so they wanted to train him as a chemical engineer. And so they're paying his full way through his bachelor's for chemical engineering. And then once he finishes his bachelor's, then they're going to pay for his master's in chemical engineering. And the reason they're doing that is because they're going to have a huge infrastructure switch. They're going to go from compressed natural gas to liquefied natural gas, meaning all the pipes are going to be changed, all the valves are going to be changed, everything's going to be changed in preparation for this liquefied natural gas infrastructure. And so the amount of energy, let's say the amount of energy per liter of compressed natural gas versus the amount of energy per liter of liquefied natural gas, there's a huge difference. And so what it's going to do is it's going to cut down transportation costs by orders of magnitude. It's going to be so much cheaper to transport in the liquid phase form versus the gas form, right? It's like
Can't you compress more gas storage?
yeah, how many PSI do you want to go? 2200 PSI, you're already looking at a heavy, thick cylinder. And if there was an accident that go on YouTube and look at that. Go on YouTube and look. There's a compressed natural gas storage facility that had a fire, and I don't know what happened. There was like a truck collision or something, and you'll see these rockets shoot out of these high pressure gas cylinders. It's amazing. It's on. It happened in the Midwest, but it's actually really scary, to think about that. And so, how many PSI do you want to go? 10,000 PSI? It's just more and more dangerous. When you work with compressed gases, you have to take a safety course, because if you have a compressed gas, you can die really quick. You die really quick is because if you have 2200 PSI of helium, and that helium purges all the air out of this room, then you're going to asphyxiate yourself rapidly. And people have died that way quickly. And so compressed gases are a bit dangerous, Well, since it's talking about compressed gases, they have a pretty good handle on these. I shouldn't say how high do you want to go, because they have this one, did I tell you about the hydrogen fuel cell, where they burn hydrogen but they convert it into electricity? Mercedes is selling a car like this, and another manufacturer is selling a car like this. But this Mercedes car, I know somebody who has one, and so I was talking to him about it. And they have 600 atmospheres of hydrogen sitting in a cylinder in the car. 600 atmospheres. And you're thinking, my God, well, 600 times 15, what is that in PSI?
9,000.
What's 15? 15 is what? 15 pounds, about 15 pounds per square inch is
It's 9,000.
per atmosphere. So 600 atmospheres times about 15 gives us 9,000 PSI. It's huge, 9,000 PSI. And so you watch that video on YouTube of that cylinder storage facility that caught on fire, and then you think about this fuel cell car, and you say, you never want to drive near one, or you don't want to drive in one because it's so scary. But so I asked him, isn't it dangerous? And he said, I said, aren't you worried about accidents? There's a collision on the freeway. what's going to happen. 9,000 psi worth of hydrogen gas. Not only do you have a compressed gas, but it's a high chemical potential gas, right? Hydrogen. Gas with oxygen is a bad mixture. Very high chemical potential energy. And he said, no, not at all. Apparently, for marketing, they took one of these cylinders, filled it with hydrogen, and dropped it out of a jet airplane, like at, I don't know, 60,000 feet or something. Hit the ground in the desert in Nevada, and nothing happened to it, is what he told me. I haven't seen that one, though. Yeah, so he feels very comfortable driving it. But anyway,
I'm gonna go back to the point you were making about how the methane and O2, like right there in the middle, the oxygen, I mean the water's at a gaseous state. And if we were to measure there, we could talk about it in liters, right? But at the end there, we have to.
yeah, this is not a gas, this is liquid. And so we need to know, but you know, you should have the density of liquid water memorized, right, to 3 sig fig.
Okay, so because there's a difference in the density at the gaseous state versus the liquid state, that's why.
Yeah, yeah, gases are typically about 1 gram per liter. Liquids are typically 1 gram per milliliter. Liquids are 1,000 times more dense than gases. 1,000 times more dense. And so that means you can put 1,000 times more fuel if it's a liquid in your tank than if it's a gas, roughly. Depends on how much you can compress the gas. Liquids aren't very compressible. But, you know, if you're just looking at, it wouldn't make much sense to put 1 atmosphere of methane in your gas tank. But let's say if you put 2,000 psi, you know, how many atmospheres is that? You know? Well, anyway, getting to this, in other words, you know, the same thing happens here. If you compress the methane into a liquid, all of a sudden you're going to go from 25 liters to milliliters. So we just finished the gas chapter, and so the gases are easy because, you know, we assume it's ideal gas. It's about 75 liters here, 25 liters here. This is liquid. Ballpark estimate. So what were we talking about?
Change in energy.
Change in energy. All right. The change in energy. So, for example, if you were to burn this in a fuel cell car, then you want very little heat, right? And you want mostly work. The work of generating electrons to push through a motor so that you can move, electric motor. And so you try to convert this energy, what we call the total energy change or the internal energy change, into work. Do you think a little bit of heat is produced? Actually, yeah, a little bit of heat is produced. It's not 100% efficient the way those motors operate. If you burn this in a compressed natural gas car, then you want to do some work. The work is, you know, pushing the pistons in the engine down, basically. And so you want, does a compressed natural gas car generate much heat? Is there a radiator and coolant water that circulates to keep things from overheating? Yes, yeah. And so, yeah, there's heat generated here and there's work. But when you want to heat up a cup of coffee here, do you want to do any work? No, you don't want to do any work. You want as much heat as possible, otherwise you're going to be waiting a long time. Right? So if you try to warm up your cup of coffee burning a mole of methane on a Bunsen burner, it'd be pretty quick. If you try to warm up a cup of coffee by burning a mole of methane in a fuel cell car, it wouldn't warm up, right? Or get that hot because you aren't generating as much heat. And so we have names for this. The total internal energy change here is what's called a state function. A state function, it's always the same. You know, the energy difference between this mix and this mix is fixed. So, delta U and U are state functions. Have you heard of state functions before? State functions, one feature of state functions is it's always the same. Always the same for given final state and initial state. It just depends on the final state and initial state. Versus, okay, we have state functions versus what we call path-dependent functions. Path-dependent functions depend on how you burn it. Path-dependent functions would be like Q and W. Q and W are not always the same. If I burn a mole of methane, I don't always get the same amount of heat. It depends on how much work is done. And so path-dependent functions depend on how the methane is used. Or burned, I should say is burned, because these are all burning methane. Burned. Oh. So let me say this. I can burn the methane here in the lab at constant pressure. Let's ignore the cars and all that stuff. Or let's say I'm going to just burn it. I don't want to do any work. I'm going to burn the methane at constant pressure in the lab, or I'm going to pull out the bomb and burn it in the bomb. If I burn it in a bomb versus burning it in the open lab, am I going to get a different amount of heat, or will I get the same amount of heat per mole of methane? It turns out I'll get a different amount of heat. Because if I burn it in a bomb, can the volume change? No. So if I burn it in a bomb, the volume's fixed. So let's say I had a 75-liter bomb. Is the bomb going to shrink down to 25 liters? No, it can't. It's got heavy steel walls. So the bomb stays at 75 liters no matter what. That means, am I doing any work? No. And that means the work term is actually 0. So if I burn it in a bomb, I convert all this energy into heat. If I convert all that energy into heat, then theoretically I should be able to heat up my cup of coffee much faster than burning it in the open lab, because if I burn it in the open lab, then I got this work term. Is that correct? Because the volume did change, didn't it? Yes? Yeah. Yeah. The amount of heat I generate by burning it at constant pressure is different than the amount of heat I would generate at constant volume. At constant volume, all the internal energy change is converted into heat. No work is done. At constant pressure, there's work. So where do I get more heat then? Constant pressure or the bomb? Obviously, you'd say the bomb, right? But you don't understand work well enough. Because do you know where I get more heat? At constant pressure. Now, why would I get more heat at constant pressure? Because isn't this already the maximum? Aren't I converting all this energy into heat? Isn't that the max? Where am I going to get more energy than this? Because delta U is fixed, isn't it? How could I get more? And so let me finish off by this. Do you see how complex thermodynamics can get?
Yes.
Yeah. It turns out that I'm not getting heat from the system. I'm getting heat from the the surroundings, and therefore I'm actually going to get more energy by burning it in the open lab than by burning it in the bomb, because in the bomb only the system can do it. And so things can get quite tricky with thermo, and so it takes time to digest this anyway.